Okay, so this is on section 8.2, and this is on the Pythagorean Theorem and its converse. I'm also going to take you through a little bit of review on radicals, because on some of these you need to simplify radicals. So you should have gotten a little bit of it in Algebra 1, but I'm going to go back and go through that. So it's Pythagorean Theorem and its converse. Okay, we've already gone through the Pythagorean Theorem, and this applies in any right triangle. And in geometry, most of the time when you label your right triangle, that right angle is your uppercase C. I'm going to label this one as uppercase A. The angles are always uppercase letters. The side opposite angle C is your hypotenuse. That's a lowercase c. The side opposite angle A is your lowercase a. And the side opposite angle B is your lowercase b. So in a right triangle, most of the time they're going to label it using the ABC. And the Pythagorean theorem, okay, this Pythagorean theorem is a squared plus b squared equals c squared. We've used that already this year, okay, for the Pythagorean theorem. Basically, what it is it takes, if you take that right triangle, the ABC, if you take the squares and make a square on each one of those, make it so it looks like a square. So if this was C and this was A and this was B, then this square is like your A by A is A squared. This square would be your C by C, or C squared, and this would be your B squared. So, in the Pythagorean theorem, example, if A was 3 and B was 4, then your C, you can solve for that. 3 squared would be 9, 4 squared would be 16, and then add them together, you get 25. And remember, when you get to that part, you got to take the square root of both sides. So square root of 25 would be 5, and they're considering the principal nth root. They're considering the positive, so C would be 5. And that's a 3, 4, 5 right triangle is one that you basically ought to memorize. That is also what they call a Pythagorean triple. Now, most people have talked about the Pythagorean theorem, but they've not talked about the Pythagorean triples. If you look on your iBook on page 1258, okay, you'll see the Pythagorean triples. A Pythagorean triple is a set of 3 non-zero whole numbers. So they're not going to be any fractions. Remember, whole numbers start 0, 1, 2, 3. Okay, A, B, and C. Okay, look up here for a minute. This is the backwards epsilon symbol, means such that. Okay, that symbol means such that. The higher you go in math, the more symbols they give you. Okay, the Pythagorean triple is a set of 3 non-zero whole numbers, A, B, and C, such that A squared plus B squared equals C squared. Okay, so the Pythagorean theorem holds for Pythagorean triples. Examples: if I said 3, 4, 5 is a Pythagorean triple, you can take that Pythagorean triple, multiply it like by 2. If you multiply it by 2, this would be 6, 8, 10. Now, does that hold? 6 squared would be 36, 8 squared would be 64. Does that equal 10 squared? 100? Yeah. Okay. Another example. If I took this Pythagorean triple and took it times 3, so that'd be 9. 4 times 3 would be 12. 5 times 3 would be 15. Does it hold that 9 squared plus 12 squared equals 15 squared? You can use your calculators if you need to. This would be 81 plus 144. 15 squared, 225. So, is that true?
Yes.
Yes. Okay. Another possible, there are several Pythagorean triples. Say I had 5, 12, and 13. 5 squared would be 25. 12 squared would be 140. If I do 5 squared plus 12 squared equal 13 squared, so that'd be 25 plus 144 equals 169. Yeah. So that is another Pythagorean triple. If I took that and say take that times 2, so that'd be 10. Take that times 2 would be 24. Take that times 2 would be 26. Does that hold? 10 squared plus 24 squared equals 26 squared. 10 squared would be 100. What's 24 squared? 24 squared, 576. 576 plus 100 would be 676, and 26 squared is 676. So yeah, it works. Okay. Another possible one is 8, 15, 17. And you could take that times 2 and get 16, 30, and 34. Last one, let's look at 7, 24, and 25. But the most famous of all these is this one, a 3, 4, 5 right triangle. That's one that you just ought to know. And that's the one that they're going to use in construction. If I'm building, think about all the things they had, all the walls they had to put up over in the new school. When they do this, if they're building a wall, they're going and they want a right angle. The way you are assured that you get a right angle, you know, put a stake in here, measure out 3. Put a stake in here, measure out 4. If this measure does not equal 5, you adjust your stake, okay, so that it does. As soon as you get that to equal 5, then you're guaranteed that that's a right angle, okay? So like if you're putting in a driveway, you know, building a garage, something like that, you always want to make sure you have square corners, okay? Okay, so those are examples of Pythagorean triples, but this is one that you should always recognize, a 3, 4, 5 right triangle. Okay, we've talked about the Pythagorean theorem up here. This one, Pythagorean theorem. Now the converse of the Pythagorean theorem. The converse, remember, they just interchange the if-then part. So the converse of the Pythagorean theorem. Okay, and it just basically says if your a squared plus b squared equals c squared, then triangle ABC is a right triangle. The other one, they gave you a right triangle and told you that a squared, then a squared plus b squared equals c squared. Okay? So that's the converse. There are 2 inequality statements. This is the Pythagorean theorem. Pythagorean inequality theorem. I should say it that way. Pythagorean inequality theorem. Okay, if they're not equal, if the c squared, if the hypotenuse squared is less than a squared plus b squared, then triangle ABC is an acute triangle. Example, like if this was CBA, and this angle then would be an acute angle. If c squared is greater than a squared plus b squared, then triangle ABC an obtuse triangle. So then you'd have an obtuse angle bigger than 90 degrees. This angle C would be bigger than 90 degrees. Okay? So you'd have something like that. Okay? This is an A down here. Let me write that very good. That'd be an A down there. So C, they're talking about angle C on those. Okay, now I want to go back and talk about radicals. Hopefully this is a review of radicals. For some of you it may be new. Okay, and if that's the case, you may have to go back on your iPad and practice radicals a little bit from your Algebra 1. Okay, in algebra we combine like terms. So like if I said 3x plus 4x, I just combine like terms and say that that is 7x. Okay, same idea if I do like 8x minus 5x. Okay, they're like terms because they have the same variable, same exponent, and I can combine the numbers in front. Well, you do the same thing when you're working with radicals. So if I had 3 radical 5 plus 4 radical 5, okay, those are like terms. Think of that radical 5 as like an x. So you combine the numbers in front. 3 radical 5 plus 4 radical 5 would just be 7 radical 5. Okay? So it's just like combining like terms. If I have 8 radical 2, to be able to do that, the radicals have to be the same. Okay? If I have 8 radical 2 minus 5 radical 2, as long as those radicals are both the same, combine the numbers in front. So 3 radical 2. Okay? Okay? Okay, that's for the adding or subtracting. Okay? Draw a little separator there. That's just combining like terms. Don't make that hard. Okay, on this one, if I have radical 5 times radical 3, they might show it with a dot or they might put parentheses around it. As long as those are both the same index, the index is this, and it's understood that that's a square root. As long as those are the same, you can multiply them together and say that that is the square root of 15. In algebra, in your algebra book, it would have looked like this, like square root of A times the square root of B. It says you can multiply those together and get the square root of AB. Okay. Another example, say I have the square root of 8 times the square root of 6. You can combine those and say that's the square root of 48. But you can't leave it like that because that one's not simplified. You say the largest perfect square inside there is 16. 16 times 3 is 48. Out of this, you can take out square root of 16, you can take out a 4. So 4 radical 3. You could have done that another way. Here's another way to work that. Same problem. Say I take square root of 8 times the square root of 6. But what's the perfect square inside 8? 4 times 2, right? So, and then times square root of 6. Out of this, what can you take out? 2. So you'd have 2, and then square root of 2 times the square root of 6. Square root of 2 times square root of 6 is square root of 12. But there's a perfect square inside there. You can go 4 and 3. And out of this you can take out a 2. And 2 times 2 would be 4 radical 3. So you get the same answer. Okay. The top method going this way. This method may be a little bit easier going that way. Multiply them together, then look for the largest perfect square. Okay. Let's try another one. So I have square root of 5 times the square root of 15. Okay. I can multiply those together and say that's the square root of 75. And then what's the perfect square inside there? 25 times 3, and out of that I can take out 5, radical 3. Here's another method. You get the same answer, square root of 5 times square root of 15. I could split this up into square root of 5 times the square root of 3. And then what's radical 5 times radical 5? Radical 25, which is 5. 5 radical 3. Okay, so 5 radical 3. Okay, so you choose which method. Anytime you have a radical, like if I just said radical 3 times radical 3, that's just 3. If I say radical 4 times radical 4, that's just 4. Okay, simplify. Okay, we've done multiplication, we had addition, subtraction, multiplication. Let's try division. If they give you something like this, 12 divided by radical 2, and I tell you this, the rule is you cannot leave a radical down in the denominator. You have to simplify it. And that holds true all the way up to calc. And then calc, we actually rationalize some numerators. So on this one, you can't leave a radical in the denominator, so you rationalize that. And what that means is you multiply by radical 2 over radical 2. So what you're really multiplying by is 1. Okay, and if you simplify, this would give you 12 radical 2 on top. Radical 2 times radical 2 is just square root of 4, which is 2. Much easier if you just go to the 2. And now reduce. This 2 would divide in there, and you end up with 6 radical 2. Okay? Let's do another one like that. If I said 15 divided by radical 3, you can't leave that radical down in the denominator, so multiply by radical 3 over radical 3. So that'd be 15 radical 3, and radical 3 times radical 3 is just 3. And then reduce this 3 and the 15, so you get 5 radical 3. Okay? Everybody okay with that? Okay, and the last kind is if they give you a quantity in the denominator with a radical. Say I give you 3 over 1 plus radical 2. If they give you a quantity or a binomial down there, you actually use the idea of a plus b times a minus b is a squared minus b squared, and that will always get rid of the radical. So if this is a plus sign here, 1 plus radical 2, you're going to multiply by 1 minus radical 2, top and bottom. Okay? So on the top, now you can leave it or you can multiply it out. If you do multiply it out, you take that 3 times both of them. Or you can just leave it in factored form. Just repeat that top part. Now the shortcut is square, because we're going to use this. I could FOIL that out, or I can just use the shortcut. Square the first one. 1 squared would be 1. Minus, because it's a minus. And then square the second one. Radical 2 squared. Radical 2 times radical 2 is just 2. So we end up with 3 and 1 minus radical 2, and it's all over a negative 1. Okay? You could then divide this out. You could simplify that and say it's negative 3 times 1 minus radical 2. Okay, and that's your answer. Let's try one more like that. Let's say I give you 6 over 2 plus radical 3. Oh, let's change that sign. Let's change that so it's minus. Okay? Okay, so what you multiply by is 2 plus radical 3, top and bottom, because what you're really multiplying by is 1. Okay? Okay, so this would be 6 times 2 plus radical 3. Square the first one. So 2 squared would be 4. Minus. Square the second one. radical 3 squared, radical 3 times radical 3. It's just 3. So you end up with 6 times 2 radical 3 all over 1. So it's just 6 times 2 radical 3. Okay? Everybody good on that one?
Can you factor that out?
Multiply it out?
Yeah.
Yeah, you could say this was 12. Ooh, no, 12. I left out the plus sign. Hang on. I left out the plus sign when I wrote that. Ooh, good thing we checked. You could multiply that out if you wanted to. You don't have to. But if you do multiply it out, FOIL it, this would be 12 plus 6 radical 3. This is the factored form. This is multiplied out. Either one of those would be correct. Is that enough examples? Rationalize it. If it's a plus sign, you're going to multiply by the minus, top and bottom. If it's a minus sign, you're going to multiply, because what you're really multiplying by, this is equivalent to 1. Okay? Okay, that's a little bit of review of the radicals.